All right, we're still working on using calculus to solve a kinematics problem. This is part 2. So this is where we do some of the typical things we do in a kinematics problem the same way we usually do. So what we need to do now is find the usual suspects, the 5 kinematics quantities, and just understand where they're coming from in the way the problem's been set up. So let's consider y initial, and the way that I've drawn my reference frame here, positive y is up, and we don't really need to regard x. It's positive in the right direction, but there's no x component here, so we're really just concerned with y. And so I'll consider this height to be the origin. Really, this ball is sitting at an imaginary origin, and so that means its initial position is 0. And without the problem giving us an actual value for the final position down here at the ground, we don't really know what to put for final position. We just know it's going to be some constant number. So I'll just write C for a constant now. It depends on how the problem's set up. It could be 2 meters, could be 15 meters, it could be whatever the problem writer says. V initial is implied in this problem because the ball or the rock is just being dropped from this height. So when something is dropped, it's at rest in somebody's hand or fingers or whatever. So initial velocity is also 0. Final velocity, we don't know. It's going to be some constant. By the time that rock lands down here at the ground, it's going to be going some speed in the downward direction. So its velocity is also some constant. And then acceleration, based on my reference frame with up being positive, I'm going to now have to name acceleration due to gravity negative 9.8 meters per second squared. And the reason I have to name it negative is because it is a downward force, and I have assigned up as being positive in this scenario. All right, now that we've accounted for all 5 of these quantities, we don't know what these 2 values may be, and we'll just leave it like that for now. Let's go and take our equation that we have over here, our position function with respect to time that we have worked out to look like a quadratic equation. Let's differentiate it, which means we need to use the power rule. And let's just remind ourselves that the power rule says if we have, let's say, 2x squared as our original function, then the way we differentiate it, find its derivative, is we take this exponent sitting right here, bring it around and multiply it by whatever coefficient is there. Oftentimes the coefficient is 1, but in this case it's 2. So that gets us to 2 times 2 is 4x. And then we reduce this exponent by 1. So I'm thinking 2 minus 1, which is really equal to 4x to the first. But then again, we never write an exponent of 1, so we'll just call it 4x. So we might say that the derivative of this function, 2x squared, is equal to 4x. So let's go and apply that same thought process to our position function up here. So the derivative, which is p prime, is how that's pronounced, derivative of position with respect to time, and we'll take this piece of it right here and take the 2, multiply it by 1/2. 2 times 1/2 is 1. So that the coefficient now becomes 1a, which I'll just write as a. T to the 2 minus 1 is 1. T to the first, I will not write that. I'll just write at plus the exponent on t is 1, so I'll write 1 times velocity initial, which is just velocity initial. Reduce the exponent on t. T to the 1 minus 1 is t to the 0. I don't need to write that because t to the 0 is equal to 1, so it'd be like writing v initial times 1, which is, we don't need to write that. And then there is there's a rule we can just memorize, that the derivative of a constant is 0. Or we could also say, well, there is really a t here. It's just in disguise as t to the 0. because that's what the exponent would be to make the t appear as a 1. So in other words, the derivative of delta y is 0. All right, so now I'm going to rewrite that, clean it up just a little bit. Position p prime with respect to time, the derivative of position with respect to time is equal to at plus v initial. Now it's usually written v initial plus at, but it doesn't matter. So the derivative of position with respect to time is equal to velocity with respect to time. So that means that at any time in this function, we can compute the object's velocity. So if we know that, let's say we want to compute the object's velocity at a half second into this, we could do that. The beauty of using the derivative is that we can use the same equation over and over again for many different values, for any value of time that we want. Okay, and so this is just how we get the kinematic equation worked around into a format that we can take the derivative.